right. Hello, everyone. Welcome to the next edition of Miton Times. Today, we have the pleasure of hosting Filip Dvořák from Filuta AI. He's going to talk about automation and AI. And so we're really looking forward to it. Please help me welcome Filip here on stage. All right. Yep, the floor is yours.
Thank you, Tonda. So today I will talk about new shifts in artificial intelligence that we have been observing during the last decade, maybe more intensively during the last 5 years. And I will try to show different angles, how we can see what is happening in AI, what is AI, and how we can, at this moment, take advantage of what is happening in the industry to choose what we want to focus on. First, it's always cute to try to define what artificial intelligence actually is and how we perceive it. This is a compilation of 3 different definitions across last few decades, and everyone is looking at AI with a little bit different, from a little bit different angle. It also changed in the past. And I like those 3 in particular. Marvin Minsky, who is one of the strong personalities in AI, identified AI as the science of making machines do things that would require intelligence if done by man. And philosophically, when we look into this definition, it's basically anything that is complicated enough can be seen as artificial intelligence. Later, it has been defined, NSTC is a council in the United States that is focusing on defining new technologies. And their definition is more modern, I would say. It's a computerized system that exhibits behavior that is commonly thought of as requiring intelligence. Similar definition, different point of view. And finally, Kevin Knight has defined it as the study how to make computers do things at which at the moment people are better. And this is adding this meta level of reasoning about artificial intelligence, not only thinking about doing things better, but also conceptually trying to encapsulate the direction. In a nutshell, I think it is good to start with having some perception what it is. And today, I find it as more of a horizon of technology. All the new technologies that are being developed are for some time considered to be artificial intelligence. When we use complicated algorithms, they are on some frontier. And the moment we understand them well enough and we can solve the problems well enough that are in that field, we just start calling it by the particular technique that is good for it. It's like the initial artificial intelligence has been focused, or some of the first aspects of neural networks have been focused on recognizing letters. But these days, almost no one calls it artificial intelligence. It's just OCR, optical character recognition. And these ways, new techniques and new fields, new domains can fit into the frontier of artificial intelligence and in some time bounce out. So for starters, I see AI as the horizon of technology, and I will treat it as such in this presentation. What I will talk about, I give a little bit of my background and what I have gone through during my professional career. Then I will look into where the money goes, because that's the interesting part. When we want to do something in AI, we have to find some application, to have funding to do the research and to build businesses around it. Then we look at the field of intelligent automation, and I will present a few interesting case studies from that field. My background, I have started at Faculty of Mathematics and Physics here in Prague. I know there is some competition between Czech Technical University and who is better and so on. I don't care. It's one of the best theoretical faculties that I could study at. Comparatively, I have experienced teaching at University of Toronto. I have been working at Stanford, and I can say that technical skill set and technical education is amazing in Prague. It's one of the best in the world. After that, I have had somewhat successful Diplomatis, I have built a logistic planner that 2008-2009 has been among the fastest in the world. I have published it. That motivated me to jump into PhD, which doing a PhD is always a question if you want to stay in academia and become a professor, or if you would rather prefer to go into industry. And then those, on average, 7 years spent doing PhD can be a little bit wasted when you compare it to the career progression that you could get. In my case, I have ended up somehow with feet in both, in academia and the industry. And that has happened mainly because being in academia and having as the largest source of satisfaction for your research a handshake at a conference after a half year of work, saying that I have done a good job at pushing boundaries somewhere, while having also lots of research that didn't find anything. I found out that I prefer to have more application, but at the same time, industrial applications can be a little bit boring sometimes when you switch into the maintenance mode. So having a feet in both has been rewarding. And when I just go through the direct experiences, I have transitioned. On my PhD, my supervisor told me I should get some international experience. And then at the end of my PhD, he told me, Filip, I didn't mean that you should spend 80% of the time abroad. But I happened to do that. I have been in last CNRS and research labs in Microsoft and Google in California. And those 3 long-term research stages were amazing experience how to get in touch with top scientists in the field. I was able to work with Malik Galap in last CNRS and creator of the modern planning. And I had pretty amazing people to work with in Google and Microsoft as well. So I ended up my PhD in Microsoft, and after that, after teaching at the University of Toronto, which was another experience, Toronto is a little bit cold, I moved to Bay Area under Palo Alto Research Center. And there I was able to secure some amazing funding from ARPA, which is one of the largest agencies that funds technological progress in US. And from there, once I got my green card, I jumped into startup scene and worked in Octon after that, and moved to Schlumberger after Octon. I have mostly been focused on, I have basically stick to one direction.
Připojoval na počítač.
We have some. Okay.
Oh.
No worries. So after within the time, I basically stick to the same field. I believed that symbolic AI is a direction that will have the most value because it's rooted in the origins of idea that we describe the world around us with symbolic models, and then on top of them with logic-based models, and on top of them we can reason about everything. This idea has some cons that caused AI winter in 60s and 70s, but it's a direction of artificial intelligence that is offering lots of answers in the field, and we will get to how we can combine it these days. But in this field, I have mainly worked on autonomous AI, which is generally AI that has to operate in environments that are either where events are happening so fast that a human cannot possibly interact and reason about how to act on those activities. It takes us 100 milliseconds if we get slapped in face, or if we kick something. It takes us 100 milliseconds to even realize that it happened. And if we need to reason in processes that take less than 10 milliseconds, we need to use some type of autonomous AI. Another situations that require complete autonomy are in operations that are too far, when we cannot communicate with the devices, which is any type of deep space exploration that has been using autonomous AI for from its inception, from its beginning. Systems like Mr. Spock are symbolic AI reasoning engines that are able to control deep space exploration for decades, and they are functional, which is amazing. And another direction that is surprisingly on the Earth for autonomy has been deep sea exploration, because when something sinks into the sea, we cannot really communicate with it. It's a very unpredictable environment because the streams, we do not understand the streams in the sea. They are just creating so much error that it's impossible to follow predictable plans, and the devices in the sea need to be fully autonomous. There is the most advanced one is in Barry in California. It's the T-Rex system. And surprisingly, the NASA researchers are providing, or they have been using same stacks, same workflow as the deep sea exploration. So this has been across multiple domains where we either require to move fast, or we cannot connect with the autonomous system, or there are too many elements for a human to make decisions upon when the data are too large. This has been my main focus for last 12 years. And we had some amazing applications. On the academic part, that's the second feat that I keep in the industry. I love those conferences because they are broad. They are not focused on single technique, and it's ACAP's largest AI planning conference. And AAAI, HKI, EKI, they are the top AI, the general AI, not in sense of artificial general intelligence, but in sense of capturing the whole spectrum that is in the field. And it has been rewarding to be able to take new research from academia into the industry. So let's get into the money. Gartner is one of the agencies that is trying to analyze, and it's probably too small, but I will. Can I zoom? I can't zoom. So I will just talk about it. Gartner is monitoring how artificial intelligence has been impacting industries, and the famous hype curve describes the process of interest that new technologies move through from some initial inception up to gaining very large momentum, which is the top of the curve, and becoming overhyped, at which moment they fall into the valley of disillusion. And sometimes this can be longer, it can be shorter. In case of the first AI wind trade has been 15, 20 years maybe. And then they get into the plateau of performance when people are actually working on the systems and trying to deliver something. We can see on this graph that machine learning, deep learning are a little bit behind at this moment, the hype. Well, behind, they have gone through the hype. And we have seen that applications that generated the cash flow, or the industry that has paid for the hype of machine learning, has been mainly marketing, and which is a binary classification problem of trying to maximize the probability that if some visitor of your web page gets an ad, you try to maximize probability that he will click on it. And this very simple business application created enormous value across the industry, and brought so much money that financed applications of machine learning across the field, even for fields that are not very continuous. Machine learning as a concept of putting curves in n-dimensional space to try to approximate some data points works really well when the problem is continuous. But lots of problems in the world are not continuous. They can, for example, if you have as an input some graph with nodes and edges, and then a single bit switch means that, for example, a flight from New York to London stops to exist, then the solutions for this problem will fundamentally change. And that's the characteristic of not continuous or discrete type of environment. There are attempts. We can see that machine learning has been even tried for operations research problems, where it's able to learn to some merit, but the performance has been definitely behind human-made models on operations research problems, and that comparison is something I will get to. Machine learning by itself is direction of technologies that, thanks to the value that they brought, they attracted a large amount of funding, and the frameworks that are these days available are absolutely amazing. Speaking about PyTorch, TensorFlow, Uber has open sourced their own framework. Out of the box, the OpenAI Gym for reinforcement learning. Those frameworks out of the box offer really lots of value, which I think has been really well spent investment. Symbolic reasoning has been a little bit behind, but we can see how it starts to pop up. We can see the decision intelligence upon the hype curve. And another very strong direction is the composite AI. Composite AI is entering the mid stage of the hype curve. And composite AI is essentially trying to incorporate operations research techniques with symbolic AI and with machine learning to solve problems as decomposition into subproblems where you use different types of AI for each subproblem. Another growing part is AI operations, where we can see that it does not only matter to create ML models that are good for showing POC, that you can get to certain accuracy on your test data and publishing a paper about it. The problem has been that the ML prototypes are not trivial to transition into industrial application, and looking at statistics, majority of POCs does not actually get applied because the results are either not reproducible or the application from the operations point of view doesn't get funded. So multiple directions are focused on trying to create operations system, DevOps around machine learning systems, around machine learning models, around platforms, around automation platforms. So from this graph, another direction is there focused on the ethical AI and human-centered AI and AI TRISM. Those are interesting, but not the prime focus. They are more of question how to administer the legal and ethical processes around artificial intelligence, which are also important, but for AI scientists, not the prime direction. So who is going to pay for the research? Intelligent automation market is predicted to grow into 600 billion spent on software this year, and the growth is still accelerating. Automation has been spreading across industries, and it became a competitive advantage. It became, as in Gartner they said, a condition of survival. And it still have required very high level of expertise, which has been a limiting factor. I believe that 2024, it's expected that AI or intelligent automation will save around 30% of costs across all operations, across all industries, which is enormous value. And those industries are going to spend on software that is going to provide the automation. So pretty nice market, 60 billion a year. There are some problems. When we look at models and when we try to understand what happens when we need to tap into the space of decisions in one model based on decisions that we do in another model, or in other words, we would like to merge their state spaces, they grow really fast. It's not just, it's Cartesian product. It's not a linear growth, but the models become exponentially more complex. And as we go further in automation, we would like more and more automation processes to be integrated into one large automation where we have the optimization space combined, and we can tap into making decisions that are more impactful. By example, we can think about a factory when you make bikes, and you need to have someone who plans how to make a bike, because you make a bike by cutting some tubes, whatever metal it is made from these days. Those tubes then need to be screwed together, they need to be connected, they need to be splintered, and so on. And this is some process that the first person responsible for designing a way how to make a bike that is going to work tasked with, and that person is going to design the process. Then this process is given to the next person who operates the factory, and that person is going to look at the actions that need to be done, and he configures the factory in a way that he will maximize with this plan how to make a bike the throughput of bikes through the factory, so he can maximize his profit. But those two people, they usually do not talk to each other at all. They just have a waterfall siloed optimization approach where one is given the output of the other, and then he builds his solution on top of it. When we are talking about merging and aggregating automations and optimization, we would like to know, when we make decisions about how to make a bike, what impact it is going to have on scheduling the bike production in a factory, and how to build machines, how to distribute machines, including inter-factory logistics, in a way that is going to maximize the throughput. And to be able to do it, we need to merge the state spaces, which is hard, difficult, and it's one of the challenges that is in front of us. Usually this is handled with linear engineering force. Let's just hire more software engineers that are going to glue it together, and then with multiple silos, we will create one large spaghetti that is pretty hard to maintain. And this is a challenge when we would like to reach the automation, when we converge, when we aggregate everything together into end-to-end optimization. This is a challenge that we need to overcome. We need to build systems that are possible to reason across end-to-end. This is hard to do in single type of AI technique. And that's my belief. And we have some options how to solve it. As I said, there are some traditional approaches. In 50s, 60s, we thought that the strips era, that there is going to be one technique to rule them all. And we thought it's going to be predicate logic with symbolic reasoning. That has failed because the world around us is just too large to describe it with predicates, and it's too continuous to describe it. If you are following Jan LeCun, he's the chief scientific officer of Meta, and he has just published his idea on how to create a complete automation system that is differentiable. Every component is differentiable, so it's possible to learn how that component should operate with some gradient-based method. Basically, let's say backpropagation using some neural networks. And this conceptual idea would allow us to model the whole autonomous system just through machine learning and few components. It's about 61 pages of ideas on how different components should operate. I did read through half of it, and also it was published just 2 weeks ago. It's a possible direction. One issue that I have seen is that there is this magic configurator that is telling all the other components how to parameterize themselves to do the learning. And it feels a little bit like constants in physics. If you remember from lessons of physics, how the constants came to be, it's usually that some scientist had idea how some process in the real world operates, And he created an equation, and then when the equation wasn't working so much, he just added some constant that was kind of eating all that uncertainty. I had this feeling about the configurator component, but theoretically, this architecture is similar to how we usually design autonomous systems, except that every part of it should be possible to learn as a neural network. So 2 directions, one technique to rule them all. We can see if it is going to produce some results. Then the opposite technique is that we should just try to connect everything together and use the silver bullet for each of the problems. I have a larger number of specialized AIs, artificial intelligences, or I probably stop using AI as a buzzword. Let's just say that we have a number of models that are operating under different premises, and those models are able to provide solutions with certain accuracy for problems, and they are the best for that particular problem. They are the best solution that we have found. That's the current statement, how we define composite AI. And composite AI, as I was mentioning, is on a large growth on the hype scale. If we go deeper into the composite AI, or generally, if we try to break down automation problems, we are still sticking to the intelligent automation because that's the industry that is paying us for doing the research. How do we break them down? So nothing new. We just look at a problem. We try to decompose it to subproblems. That's something that we can do summary it automatically, but most of the time it's very hard to do it automatically, and we need to have some human intelligence involved to understand, based on expertise, how to break the problems the best. But once we break it, we keep breaking and transforming the problem until we get to a level of problems that are directly mapped to some solvers. And then pretty easy, we go with a new problem, we bubble it down, solve it, bubble it up, transform it, and we have the solution of the original problem. And the quality of this solution is only as good as our decompositions are. It's generally hard to make decomposition that is that doesn't impact our optimality space. Those perfect decompositions are very rare. So often we have to work with some greedy strategies that we have some estimates for, and we can at least in this decomposition calculate how much what is our theoretical distance from the optimal solution. It's we are forced to use non-optimal decomposition because computationally we still cannot solve the hard problems that are first of and at the top, and that are even at the ends, but at least at the ends, at the leaves of the tree, we have problems for which we have good dedicated solvers. Then the decomposition itself, it's a form of art. It's based on experience. To some merit, it can be learned by machines, but mostly the decomposition is what these days intelligent automation consultants do. When we look at the models that we can use, there is really lots of research on how to understand world through some mathematical structures, and how to try to reason on top of them and solve problems that are in that particular field and that particular model. Personally, when we look at new space, new problem, new domain, new industry, we can start by trying to find parallels in the research, try to find the best fitting theory that has had the most development investment in recent years, and then try to apply it, see what results we get. And this is kind of empiric approach, where we try to leverage as much research as has been done recently, because most of the time we would like to use the technique that is the most appropriate, and the techniques that are the most appropriate are techniques where we have had seen similar applications before, and that have had enough development time invested recently, which makes machine learning pretty amazing because everyone was working on machine learning and it's really good at solving continuous problems, but it cannot scale for any operations research problem. When we look at real world problems, most of the time they can be seen as some interleaved nested models from the classical mathematical structures that we identify here as complex systems. This is categorization from Wikipedia. It is changing in time. There have been initiatives how to create ontology for all decision-making and modeling problems. And those ontologies are a little bit hard to look at. They are, because there are so many different research papers that are creating models that can be applied, may not be applied. It's generally a problem of itself, how to categorize all the existing models in the world. We can, the best approach from my experience is to just treat it as a toolbox. You have a toolbox that has a certain amount of tools and you get good with certain tools. And there are tools that you have never used that you may use in the future. And maybe you can create that expertise on how to using the tools in your team, which is one direction if you want to be general, to cover as many tools as you can. My experience personally with I have deep experience when I was myself trying to understand what I can work with, maybe with application of 5% of the modeling techniques. And I have some view of how about 80% of them work. So I can dive deeper if there is something that is similar. The problem manifests features that are similar to work that has been done for the particular modeling. Let's look at how an example breakdown can look like. So this is a practical breakdown of autonomous operations control that I have deployed in real world life critical applications. And the breakdown is pretty straightforward. We are solving some observation problem, diagnostic problem, recovery problem, which is reactive planning, basically, a deliberative planning for long-term planning and optimization, which requires some decomposition, and then we need to execute. When we know what to do, we need to be able to execute the actions and communicate with the world around us. There is we can see the DOM1, DOM2. Those are domains that we communicate with. We assume that there are multiple actors in the system, and we have an interface with all of them where we tell them what to do. That's what the dispatcher is doing, sending commands, and they tell us how they see the world, which is what's happening in the observe component. And then everything else is broken down to atomic solvers or other techniques. We can see that, for example, some domain can in this case we put camera on a certain piece of physical hardware. And we have taught a neural network how to identify behavior of that hardware, which was projected either into certain scalar value or into a failure. And that was the atomic information that was going up as an observation. Similarly, in this system, there have been about 60 different domains, components that were telling us what is the state of their hardware that they are monitoring. And on top of that, I have been building a planning system that has been able to plan in a horizon of hundreds of actions, how to achieve the goal in the most optimal way and guarantee that it's going to be achieved, while the recovery strategies have been written as reactive behavior, as behavior trees. So this is example how of one application, or I would say a blueprint, how to break down the automation control problem. For some details, for explanation, I have used standard CP solver from OR tools, and on top of that, I implemented quick explain, which in case that something breaks is going to identify the smallest, the minimal critical set, with the smallest set of rules that if we take them out, the problem becomes consistent again. And for the decomposition of the planning problem itself, I have just taken out all the difficult parts. There was some hidden TSP, traveling salesman problem that planners as a logic reasoners are not really good with. So you just decompose, take it out, and solve it with some greedy approach, which is reasonably fast. This whole system has been able to operate at different, I think we were at 100 milliseconds operation latency. Let's look at some use cases, what I have worked on. This was a company that I have built engineering team for in San Francisco, and it was a really fun company, kind of side project where we were delivering tea on time within mostly 20 minutes. When you order it on app, then we started adding cookies, and the tea itself has been mixed in the trucks. So the moment it arrived, my dispatching system took the order, it assigned it to a particular truck, and those trucks started making the order. And then within that problem space, the trucks were arriving to destinations, to the addresses, and baristas. We were hiring lots of people from Starbucks, and they have had the experience. We also called them artists because they were drawing on the cups, and they were delivering to their destination the tea. So classic San Francisco stuff, startup. It was fun and nice example of intelligent automation. Next one was Octon. That was my full-time startup. And we have started with a pretty small team in 7 people. And we focused on building operational system for factories that are made of 3D printers. And this challenge has been reasonably large because the problem space included continuous problems. It included problems to, unnecessary clicking. It included problems how to, when you are 3D printing in some limited volume, how to position the unique pieces that you 3D print in a way that they do not cause warping on each other, and how you do 3D bin packing so you can actually put as many of them together in the 3D printer. Then all those have expiration times. All of those need to be delivered to the customer, and you are also solving job shop problem because you need to schedule it the best possible way on the factory and on the machines according to occupation. And this nested problem then has been leveraged first for quotation because I was able to compute in 2 minutes when an order has arrived, the request for quotation on how much it is going to take to build it at this current state of the factory. And second application of the system has been to understand when something breaks, when a machine breaks. So first of predictive maintenance, to know what's the probability that it will break, and if it breaks, how to quickly replan everything that machine has been doing so we can finish the operations. This has been pretty successful because the business model just charged for each connected machine. And we have exited this one last year in September for 180 million, which was a pretty nice exit. Next application are in cloud kitchens. And in this case, we work with the largest cloud kitchen operator in Eastern Europe. The cloud kitchen is a concept how to aggregate multiple gastro businesses together when you share the supply chains, when you share the operations, how you make the food, and when you share the dispatching. The problems that are manifesting the most are the supply chain and restocking planning, demand planning, which are continuous problems in nature, dynamic pricing, mostly continuous problem mixed with some operations research because we need to build a predictor that is going to tell us based on demand prediction, if we increase the price, how it's that demand going to reduce, and then find some optimum, how to price the items so that we have the largest multiple between demand and our price. Also understanding how long it's going to take us to make a meal, is a surprisingly hard prediction problem, and there is a dispatching. So being able to solve this end-to-end is interesting challenge that we have started working on. In oil and gas, that's one of the motivations that I had from past few years. We were able to deliver automation systems that are achieving very high level of autonomy with some remote overtake in life critical real-time environments and several layers of automation. The closest controls to hardware are working at 1 nanosecond response time. Then the controllers on top of them, PLC controllers, are working at 1 millisecond, and the total umbrella for high-level decision making has been 1 second. We are ticking the behavior trees with 100 milliseconds, but officially the response time is 1 second. This application has been amazing. It's state of the art in oil and gas and growing rapidly. This is the end of my presentation, and I would like to ask both everyone who came in person, thank you for coming, and people online for questions.
Yep, let's thank Filip one more time. And if you have a question and you're here in person, I'm just going to hand you the mic. If you're online, feel free to unmute yourself. We should be able to hear you. I'm sorry? No, it was not forced. It was just once they can unmute.
I'm curious about the technical part. So I understand that you're basically proposing to decompose complex problems into like simple problems that we can solve, and you basically say that we can even I assume in some cases do it in a form of a directed acyclic graph.
Yes.
But do I understand correctly that the directed acyclic graph counts for basically the problem definitions, but not for basically the computation of the final value based on the subproblems? Because I assume that well, here you say that composition is a Cartesian product of the modal spaces, but this is something intractable that you probably have to do in a smart way, right? And I kind of assume that this is the main magic of building these systems.
Yes, that's the artistic part, and it takes lots of research to do it well, and at the end also intuition. And sometimes I experimented and worked with hybrid techniques when you can, to summarize it, have, for example, something like Monte Carlo tree search, and that Monte Carlo tree search gets delayed feedback from another solver that is providing resolution for subproblems, and you can slowly start influencing the Monte Carlo tree search to explore the areas that are going to be more rewarding. This is the hybrid. I do not have strong results saying that this works really well. It's more that this is the only experience when I saw a hybrid where you are exploring multiple spaces at the same time. Everything else is just hierarchical decomposition, where you try to have the technique that has the largest impact or the top level problem the highest and make those decisions on the top.
So if I may follow up with another question. So from the applications that you have shown us, they're amazing. The artistic part of basically composing back the outputs of the solvers and sub problems was mainly done, say, by hand and intuition, or are there some like standard techniques to look up to in case that we would meet such problem?
We have reached a moment where all the components, all the nodes became microservices, and at that moment the protocol that defined their communication has been just protocol buffers, and we still had to define the protocol buffers, but all the extra workaround has been done just by compilation, by automated compilation of the microservices.
Actually, I didn't ask so much about like the implementation level, but rather the design level of, you know, how to combine the outputs in the smartest way, right?
Yes, there is when you approach a new problem, you basically have to do it from scratch. But the problems start to repeat, and once you see enough domains, for example, in the AI planning community, there are models for hundreds of different different domains where industrial problems, where people just came and they modeled it as different types of predicate logic problems. And you can, predicate logic is amazing that you can project it into multiple other problems. We are staying within some p-space hardness or NP hardness. And that allows you to take, for example, planning, and almost anything can be projected to planning. In the NP space, almost anything can be projected to constraints or satisfiability. So this helps a little bit through reusability. But answer to your question, if you come to something completely new, you have to sit on it and solve it yourself.
Thank you.
So are there any more questions?
Oh, just a follow-up question actually about this question, how to identify the proper technique for a particular sub-problem. I guess that applies like to how do we actually model a certain domain, but I'm assuming like the nature of a certain sub-problem may be discrete or continuous by itself, and I'm guessing this would inform the decision which technique to apply. So the previous answer was rather like, okay, if I'm going with a discrete approach, there are still multiple ways to do it, and it's kind of a matter of experience. But there can be, if I understand correctly, some like hard criteria that inform whether a discrete or a continuous technique should be applied, and it kind of goes back to the composite AI. Is this correct?
That's absolutely correct. We can encounter problems that are easy to be characterized, even automatically characterized as strongly continuous or strongly discrete, and then it basically creates a switch in the toolboxes, which techniques we want to use. And during the decomposition process of trying to find out what is the dimension of difficulty, because we are when we approach a new problem, a new industrial problem, the first thing that we need to identify is the hierarchy of dimensions of difficulty by their importance. The same problem can be hard in many different ways based on who. It can be, for example, you can have trucks that are moving orders around, and you can come to a company that doesn't. And in their case, the important part is going to be how. And you are going to be solving the next problem, and that's going to be very contained. Priorities, how you are solving the problem. And in that case, the hierarchy could be started. But exactly the same problem.
I'm sorry, I think we have an issue with the mic right now. I think the batteries ran out. I'm going to hand you this one. Just we should switch this one off first. And yeah, you can.
The key is to identify dimensions of difficulty when we are solving a new industrial problem. And as you have mentioned, Martin, this is the next stage in using our toolbox would be to understand the problem space, understand which problem is, which dimension of difficulty is providing the highest value. Then we can start picking the right solvers that are good for that dimension of difficulty and starting to think how to combine them together. And it can be in continuous space. We can. It's very, very easy these days to see automation where we need to combine image recognition to understand what's happening around us. We have autonomous car. That car is approaching a crosswalk, and we have some point cloud, and we built a classifier on top of it that is telling us if there is someone walking over the crosswalk or not. And that classifier is going to be, in this case, at the bottom, and is going to provide the value to the top level decision-making system that is going to understand that if someone is crossing, then we should stop. And then it's going to engage another system that is at low level, and that's going to apply brakes in a way that is not going to create too much G to make it uncomfortable for passengers inside, for example. So these breakdowns of the problems and dimensions of difficulty are probably the two high-level meta-reasoning approaches how to do intelligent automation, which has been my practice for last 12 years. When we then, just to follow up on the example with the trucks, one company is solving bin packing problem, and on the top they have the bin packing, putting objects into the trucks as the highest dimension where we save the most. Another company is doing absolutely same business, absolutely same problem, but their highest dimension of difficulty is, let's say, Hamiltonian. You need to solve the traveling salesman problem because it's a company that is, let's say, operating in some countryside area and the distances are much larger, while the first company has been operating in a city. So this needs to be adapted, and it means that you actually have to do breakdown based on your data. And you should be able to make the breakdown and maintain the breakdown, the composition of problems, as easy as possible and with as minimal expertise as possible.
All right.
So how do you test these designs? So you are designing this breakdown into the sub-problems. Do you, for example, at the beginning, try multiple ways how to solve the problem and then somehow test it, evaluate it, compare it? Or is it is just one shot?
Sorry.
Absolutely. It's the standard model, test, iterate, and like everywhere in designing models. It's just because it's a model that is a breakdown of other models. We do not have better solution. We can just try to save our time and speed up this process and reduce the cognitive complexity. So you don't need to study, let's say, constrained programming on a PhD level to be able to solve a problem with constrained programming.
All right, I think we have space for one or two more questions, if there are any. Yeah, go ahead.
So could we go quickly through one of those examples? One more example, you mentioned this breakdown for this traveling company, transportation company. Could we do one more of those examples? Problem breakdown.
Right. Do you speak about the example of the distribution company that has trucks and that is packing items into the trucks and the trucks are traveling around the city? Or
so how the problem breakdown of the subproblem looks like, for example, this or some other company?
Right. So in this case, the top level problem, the dimensions of difficulty basically showed that the most important part is the logistic part around San Francisco, because it was really congested most of the time, and people usually made orders when there was a peak and it was hard to get around. So the top level problem has been the prediction of traffic, which was outsourced. And on top of that, on top of those predictions, it was just shortest paths that led to Hamiltonians, how to move around. And Hamiltonians basically meant that the truck at some moment was running out of resources, and you were trying, given your current orders, to find for all tracks the smallest sum of all Hamiltonians that the tracks need to do to deliver the orders. And at that moment, the difficulty of resupplying wasn't that hard because the trucks were usually stuffed with enough material, so they had to resupply maybe only once or twice a day. And we could plan it, we could predict it pretty well. We also were working with some splitting and truck exchanges, which meant that some trucks, when they were close to each other, and one was running out and it was too far to get back to base to get more supplies, the trucks could exchange the resources. It complicated the problem, but it opened a more optimization space. At the end, the gain was minimal. It was more of an experiment, and it was cognitively complex for the baristas to do those exchanges. It was just complicating their job, so we didn't do it so much.
All right, thank you very much. So I think we're running out of time a little bit, so let us thank Filip again. And a little bit of information. We are going to announce the next Miton Times on Meetup.com again. And thank you all for coming, both in person and online. See you next time.